Hello, Stats class. Here's lesson 8.3a. We are going to shift gears today. And first I want to talk about the difference between 8.2 versus 8.3. So 8.2 we were working with proportions, which is one of those two really common estimators that we talked about. And then in lesson 8.3, we are shifting to doing means instead of proportions. And so that's kind of a big shift. We've seen some stuff with means before, and so some of this won't surprise you, but let's just kind of summarize that. In 8.2, we were using p hat to estimate or predict the value of p, which is the population proportion. We're going to change to using x bar as our statistic or estimator to predict the population mean, which is mu. Remember, that's the Greek letter mu. We are going to change a few things about what we do. The main thing that changes in the conditions is the normal condition is a little bit different. The other two stay the same, which is kind of nice, but proportions are normal if NP and NQ, and we had to use P hat, remember. NP hat is greater than 10, and NQ hat is greater than 10. There is no P and Q in means, and so we can't check that. We're going to change to checking the sample size only. And you might remember this from chapter 7, that we're going to say if the sample size is greater than or equal to 30, we're going to call it normal enough. Or it's also possible that the population might be normal in the first place, and if that is true, then the sampling distribution would also be normal. Sometimes that would be given to you that the population is normal. And if it's not, then we're going to check the sample size. And there's one other method that we'll probably learn in the next lesson, not today. And then the standard error in our formula is going to change also, because instead of doing square root of p hat q hat over n, which we did for proportions, we're going to change to using the formula for means, which is the population standard deviation divided by square root of n. So now what's interesting about that is that population standard deviation will not always be given to you. So we're going to talk in a minute about what to do with that. The most common reason you will be given this population standard deviation is for this first type of problem I want to talk about first. So we're going to do this first, and then I'll talk about what if you don't know that sigma value. So the new formula, I'm not going to write the old formula. Just the new formula that uses this standard error is we're going to, instead of starting with p hat plus or minus, we're going to start with x bar plus or minus. And we'll have our z star critical value, and we'll have our standard error, which is sigma over square root of n. So that's basically the formula you would use for means instead of proportions. It shouldn't look surprising to you because you've seen all three parts before, but this changed a little bit and this changed a little bit. And I want to remind you that this piece right here is called the margin of error. It's how far above and below your estimate you're going. So this little picture is still here. We're still doing this. We're taking our point estimate, which is now x bar, and we're going, this little bit is the margin of error. That's how far below and how far above you go from x bar to get your interval. And what we're going to do is the same as what we did with proportions. We're going to say that we are 95% or whatever percent sure that the true value of mu is somewhere in this. We're whatever percent sure that mu is in this interval. And we're going to do that just like we did with proportions. It's just the calculations are a tiny bit different. All right, so the type of problem I want to talk about first is the reason I started with sigma being known. We're going to come back to sigma being unknown very soon. But if sigma is known, the only type of problem I've seen that in on the AP test is if they're asking you to find a sample size. So that working backwards thing that we did at the end of 8.2, we're going to start with that in 8.3, finding a sample size if you know all the other information in this formula. You'd have to be given the margin of error, and you'd have to be given sigma, and then you could find sample size, which is n. So we're going to do a problem like that first, and then we'll get to the more realistic situation, which is what if you don't know sigma? So to find a sample size, let's say we want our margin of error to be less than or equal to 1, and we know that our sigma is 5, and we want to have 95% confidence. So here's an example of that. That allows us to find our z-star, which hopefully you have this one memorized by now. Z-star for 95% is 1.96. You'd get that by doing inverse norm of the 95 plus half the extra. I'm not going to put that picture again because I think we've seen it enough. Let me know in class if you need me to say it again. So Z star is 1.96, and I'm going to take all of this information and plug it into the formula for margin of error. So my margin of error formula is this Z star times sigma over square root of n, and it has to be less than or equal to 1. They told me that's my margin of error. And so let's start plugging things in. We know what Z star is. It's 1.96. We know what sigma is. It's 5. And then square root of n is what we don't know. And this is like we did before. We're just solving with algebra to find n. No problem. You can handle this, right? You multiply by square root of n on both sides. That cancels. You divide by 1. Oh, that's really exciting, isn't it? You're not always going to divide by 1. Sometimes it'd be something else. So I'm going to go ahead and divide by 1, even though it doesn't do anything. And then to get rid of the square root, you have to square both sides. So I ended up with n is greater than or equal to, I like to move the n to the beginning. And if I type this in my calculator, 1.96 times 5, and then square it, I got 96.04. And remember, we always round up on this type of problem because of the greater than or equal to. And just like we did when we did with proportions, you could go through this algebra process every time, or you could just memorize a new formula. So here's a little bit of a sidetrack. Where'd this n come from? N has to be greater than or equal to the z star times the 5 was the sigma. This 1 is the margin of error, and you just square that whole thing. So if you would like a new formula, there it is. Or if you're comfortable doing the algebra every time, that's also fine. That's the formula that you would use to find a sample size given a margin of error and a sigma value. All right, so that's kind of like what we ended 8.2 with. We did that working backwards thing last. The reason it's first here is it is the only time, I'm pretty confident I can say this, that on the AP test, they will never give you sigma unless it's this type of problem. I've never seen them do it before. If they do it in the future, I'd be very surprised because it is really unrealistic to know sigma. So let's talk about that. I used to spend a couple days on problems where we knew sigma, and then I revealed the fact that we would not usually know that. And this book actually goes straight to this, so I'm going to do it their way. I like it better that way because it's so unrealistic. On books and on tests, and anytime you're doing math from a book, you are sometimes given sigma. But in real life, sigma is the population standard deviation. And how in the world would you know what the population standard deviation is? That is really unrealistic. So I'm just going to tell you this doesn't happen when you're doing statistics for real with real data. It just doesn't happen. So what I like to do is I like to pretend that this sigma that they sometimes give you if you're doing this type of problem, this sigma comes from a mysterious stats fairy who comes and whispers it in your ear and says, oh, by the way, sigma is this. And that's so unrealistic. But you know, and when I used to do this with like spending a couple days on it, we kept talking about the stats fairy, and then one day the stats fairy would not show up. And I'm just going straight there. Usually what happens in real life is we don't know this. And so I'm going to say the stats fairy is really hard to get a hold of. She takes days off all the time. In real life, she's not going to show up. She's not going to show up during the AP test. I'm sorry. Usually we don't know sigma. the fairy is lazy, or the fairy is taking a day off. And we're just not going to be able to rely on that fairy. I'm sorry. It just isn't going to happen. So what do you think we would do? If we were in class, I would ask you to tell me. And I hope somebody would say, well, if we don't know the population standard deviation, then maybe we might be able to use something else that we could get from the sample. And I hope somebody would think of this and say, oh, well, maybe we should use the sample standard deviation, which is called S. We're going to use S to estimate sigma. And that's the sample standard deviation. We have our sample. We could take those numbers in the sample and figure out the standard deviation. So now, here's where I often play a game in class, and it's kind of fun, and we're not going to be able to do it this year. I'm so sorry. I have a program on my calculator that I would give to all of you, and I'd have you try it. And I'm just going to talk about it instead this year and say, okay, here's our normal curve. Here's our z-score of 0 and a z-score of 1 and a z-score of 2 and -1 and -2. And we are going to think about how often would we be in these rare event areas. So this area and this area, this in the middle is supposed to be what percent? I hope you would tell me that it's 95%. And that this and this are the 5% extra, which means it's 2.5% on this end and 2.5% on this end. And we've talked about that before, so that shouldn't be a surprise. If we were doing this in class, we would be generating random z-scores over and over again to see how often that 5% feels like. How often do we get to above 2 or below -2? And we would be calling out bingo or something like that every time we got it. I'm not going to try and do that on the video because I don't think it'd be as effective, but I'm just saying that this should be 5% of the time, right? Okay. If you use sigma, it's 5% of the time. If you use S, you end up in these outer regions more often than you should. And so what happens with S, this is the normal curve. But what happens with S is you end up over here more often than 5% of the time. And so it ends up flattening out the curve a little bit. Gee, that sounds like COVID. Oh, gosh. So this outer edge is thicker and more common. These rare values are more common when using S instead of sigma. And I'm just going to have you trust me on that. I'm going to try to find a way to put it in a warm-up or something. I haven't worked that out yet. I have a couple more days before you do this lesson. So we'll see. But this, because of that, somebody invented a whole new distribution that's wider and has these heavy tails that happens when you're doing S. And that allows us to still be able to calculate accurately. So the normal curve is this skinnier one that has the skinny tails. The fatter, wider one is called the T distribution. And it was invented for this purpose. And so to remember which one it is, the normal curve is slim or slender. I call it Slim Z. Yeah, I guess I would start Slim Z versus, I call it Tubby T. T's a little bit wider and fatter and has more stuff on the outside and less stuff in the inside, and that's the main thing you need to know about it. And we're going to use that whenever, we're going to use the T distribution whenever we use S instead of sigma. So because T was invented for this purpose, you use, if you know sigma, which is the population standard deviation, and this is what you use if you don't know sigma, and therefore we're replacing it, we're estimating it using S. So it's not quite as fun as what I usually do in class, I'm sorry, but you're still gonna need to know when to use which one. And we use this one all the time with proportions. We use Z and the normal curve. because we can calculate a pretty good estimate of sigma based on the p hat q hat over n, which is a better estimate than s over square root of n. So we're just, when it's proportions, we're going to use this. When it's means, we're almost always going to use this. And so, and this is another way of saying the tubby T is it's called a heavy-tailed distribution. It just has more values in the tails or in the outer regions. So when we replace sigma with S, we get another new formula. And we end up doing X bar plus or minus, instead of Z star, we're going to use T star, which I'll tell you how to find it in a minute, times S over square root of N. So this is our new critical value that we need when we're replacing with S. Now, if you have a graphing calculator, if you have a 1980 TI-84, you are in luck because inverse T is one of the things on this calculator. So I'm going to show you that, but I'm going to tell you if you have an 83 or any other type of calculator, you might not have this. So second vars, go down, and right after inverse norm is inverse T. So if you have a TI-84, TI-84, you'd go to second vars like usual, and you would go to inverse T. And you'd have to put in two numbers, so instead of just one, so that's kind of annoying. The area under the curve is still the, I'm going to call it 0.975 because that's what you would use for the 95% plus half the extra that we've seen before. And then you have to do the second number that's called DF. So DF is degrees of freedom. I'm going to put DF here, and then I'm going to explain down below. DF is called degrees of freedom. We're going to see a lot of that later in the book. Right now, you're going to just learn this type. So degrees of freedom for this chapter is n-1, and then later on we'll talk about how sometimes it's something different. It's technically the same thing you use if you are dividing by like in the standard deviation formula, you divide by n-1 instead of n. It's the same concept, and I'm not going to spend a lot of time explaining it today. But you can enter, like let's say our n was 30, so we would put 29, and then you get your T star by doing that. And it's T star is 2.045, which is different than if you did inverse norm. If you did inverse norm of 0.95, we already know that we get 1.96. So basically, T star is further out. You have to go further out to get that 95% than you would if you were using Z. So that's a little bit weird. If you have a TI-84, you're going to do it that way. If you don't have a TI-84, then you're going to have to do it with an online method. And there is a way using GeoGebra, and I will show you this in class because I think that's easier than doing it on this video. GeoGebra probability calculator. Basically, instead of normal, you would choose the T distribution in GeoGebra is called student, because the guy who invented this published under a pseudonym of student. So you would do the student's distribution. It's the student's T distribution. Or just choose student, and then you do it the same way you do it with the normal curve, where you would have to move the T value until you got to the right percent. And like I said, I'll show you that in class because I think that's easier than on a video. So we will do some more of this on the next few days, and we'll practice it a bunch of times. There is also a table B in the back of your book that you're welcome to play with that also does the T distribution. So I might put a little bit of that in the next video. Actually, you know what? I could show you that right now. So, this video is almost should be done, but I'm going to show it to you anyway. If you are totally stuck and you don't have anything to use at all, I'm going to find table B in the back of the book. You already are familiar with table A, which is standard normal. There's the second half of table A. Here's table B. And what you do with table B is you look for the 5%, or the 2.5% would be for 95% confidence, right? Is whatever this upper tail is. And then you go down to the DF that you need. So like that one that I just did, DF was 29, and I would go over here, and there's the 2.045 that my calculator gave me. If you want it to be even easier, look at the very bottom of this table. That same column I was just on ends with 95%. So you could do that, and 2.048, there's your T star. So that this gives the most common confidence levels and the T stars that you need for those. So that's your alternate method if you don't have a TI-84, but that's okay. All right, that's enough notes for that, and we will come back in the next lesson and do some more.